So we've been talking about how to solve this differential equation here, and I've just re-expressed the steady state membrane potential as this expression here. And in this video I want to show you how the system behaves, just to give you a little bit of intuition. I've posted some code using some Python code that will actually run these simulations for you. So if you know how to code in Python, you can actually look at the system and play around with it yourself, and that's probably the best way to learn this. And if you don't know how to code in Python, I definitely suggest that you pick it up at some point, because it's extremely useful, especially if you're interested in computational neuroscience. So down here I have one example simulation that I ran, and in all these traces the red line at the bottom is going to show the injected current. So this is my INJ. And the top trace is going to be the membrane potential, or V. And I'm just doing a simple step current here. I'm starting at 0 nanoamps of current, and then stepping up to 3. And as we talked about before, the membrane potential is not going to approach steady state instantaneously, so the steady state is essentially this value over here, but it's going to slowly approach it in a curved manner. And the steepness of that curve is going to be controlled by the time constant. So it's nice to sort of start with something simple like this. We've already talked about why this should be the case, so the fact that the numerical simulation is actually giving us this result is promising. One thing that I do want to point out in this simple example is that if you pretend that this is an experimental cell and you're applying some amount of injected current, you can actually estimate the capacitance of the cell and the resistance of the cell in the following way. First, you can estimate what the time constant is. The time constant is going to be the amount of time it takes for this membrane potential to reach, what did we say, something like 2/3 of its final value. So this is roughly the time constant, something on this order here. So once you estimate the time constant in this way, then you know tau equals RC, and you already have a value for tau. And then the second thing that you can estimate is the steady state voltage. And steady state voltage we know is equal to E plus Ri. And I'm just going to circle all the things that we can measure. So we can measure the time constant, we can measure the steady state membrane potential, we can also measure the resting membrane potential, which is just down here. And then finally we can measure, or we decide how much current we want to inject. In this case it's 3 nanoamps. So I'm not going to go into it, but you can just, in the simple experiment, you can actually figure out what the resistance and the capacitance is. You can figure out the resistance from the steady state voltage, and then plug the resistance into this equation to figure out what the capacitance is. If you were actually running the experiment, I should make the disclaimer that you probably would want to do several trials of an experiment like this, because in any experiment there's going to be noise and sort of other uncontrollable factors. So you would want to replicate this experiment several times and maybe look at different levels of injected currents, and that'll sort of give you an estimate of what the input resistance and the capacitance of the membrane are. And actually, to really accurately estimate the capacitance of the membrane potential in biological cells, you usually use a technique called voltage clamp. But just theoretically, you can calculate both the time constant and the resistance from this simple experiment. So just to build this up one further step, this is the previous trace that I was showing you before. And this had, I just picked a value of resistance that was somewhat reasonable. And then in this trace, or this experiment over here, I changed a parameter. And what parameter did I change? Well, if you actually just look at this, you can immediately figure out what it is. So maybe pause the video and think about what parameter did I change to change from this behavior over here to this behavior over here. And if you look closely at the steady state membrane potential, the steady state membrane potential is around 50 millivolts over here, and the steady state membrane potential is negative 30 millivolts over here. The two Y scales are different. So if the steady state membrane potential has been increased by so much, then I must have increased the input resistance. So this is just a simple example of what happens when the input resistance increases. You see an increase in the steady state membrane potential, and you also see an increase in the time constant. So here we approached steady state very quickly. After 60 milliseconds we were roughly at steady state, and over here at 60 milliseconds, we're definitely not very close yet. So that's what happens when you increase the input resistance. So what happens if we decrease the membrane resistance? Well, if we decrease the membrane resistance, you'll see that the steady-state voltage has now significantly decreased to, in this case, 57 millivolts, whereas before we were up at negative 30 millivolts. So the steady-state membrane potential is decreased, which makes sense, and we also have decreased the time constant, so we are approaching steady-state a whole lot quicker on the right. And if you download the code, you can sort of play with this, and you should get similar results, and perhaps gain an intuition about this system. So this is just a very simple, just sort of introducing you to the code and simulations. And in the next video, I'll sort of go into a little bit more complicated injected current inputs into the cell, and sort of continue down this same path, just playing with the system and seeing what it gives us. So I will see you in the next video. Thanks.